In 2013, astronomers scanning gamma-ray bursts across the distant universe found something that should not exist. A concentration of cosmic explosions spanning 10 billion light-years, so enormous that light leaving one edge when the universe was young would not reach the other side for another 10 billion years. If confirmed, this structure dwarfs everything else ever detected. It challenges the most fundamental assumption in cosmology, that the universe looks the same everywhere when you zoom out far enough. Scientists are still fighting over whether it is real. The answer could rewrite our understanding of how the cosmos organized itself from nothing into everything we observe today. If you enjoy exploring discoveries that push the boundaries of what we know about reality, smash that like button and subscribe. It genuinely helps more than you might think. Now, settle in and get yourself comfortable. Let's begin. For most of human history, astronomers assumed the universe was smooth. Stars gathered into galaxies, and galaxies drifted through space in a roughly even distribution, like dust motes suspended in still air. There was no reason to suspect otherwise. Every telescope pointed at every patch of sky showed galaxies in every direction, at every distance. The cosmos appeared uniform, democratic, featureless at the grandest scales. This assumption was not just convenient. It was enshrined in physics as the cosmological principle, the foundational idea that no location in the universe is special. Look far enough in any direction and you should see approximately the same density of matter, the same number of galaxies per cubic megaparsec, the same general cosmic scenery. A civilization living 10 billion light-years away should observe the same statistical distribution of galaxies that we do. The universe, at sufficiently large scales, should look the same everywhere. The principle simplified everything. It allowed cosmologists to model the entire universe using elegant equations derived from Einstein's general relativity. It let them assume that measurements made from Earth applied universally. It reduced the terrifying complexity of a cosmos containing 2 trillion galaxies into something tractable, something a human mind could model on paper with a pencil and a few constants. It was beautiful, efficient, and for decades apparently correct. Then astronomers started counting galaxies properly, and the elegant picture fell apart. The problem was distance. When you photograph the sky, you see galaxies projected onto a flat canvas. 2 galaxies that appear side by side might actually be separated by billions of light years, one far behind the other. A galaxy that looks like it belongs to a cluster might actually sit in the foreground, unrelated to anything around it. Without knowing how far away each galaxy actually is, you cannot determine whether they cluster into patterns or scatter randomly. Early galaxy catalogues were 2-dimensional maps of a 3-dimensional cosmos. They were like aerial photographs of a city taken from so high that buildings, parks, rivers, and parking lots all blur into a flat grey mosaic. You can see that something is down there, but the structure remains invisible. You cannot tell a skyscraper from a pond when everything flattens into a single plane. This limitation frustrated astronomers for decades. They could see galaxies everywhere. They knew galaxies formed clusters. They had catalogued rich clusters like the Coma cluster and the Virgo cluster since the 1930s. But the overall 3-dimensional arrangement of matter, the grand architecture of the cosmos, remained hidden. It was like knowing that cities exist but having no map showing how they connect into nations and continents. You can study individual buildings without understanding the infrastructure linking them together. The breakthrough came from redshift. When a galaxy moves away from us, the expansion of space stretches the wavelengths of its light toward the red end of the spectrum. The farther away a galaxy is, the more the intervening space has expanded during the time that light spent travelling, and the greater the redshift. By measuring the precise colour shift in a galaxy's spectral lines, those characteristic fingerprints of elements like hydrogen, calcium, and sodium, astronomers could calculate its distance. Not perfectly, not without error margins, but well enough to place each galaxy in 3-dimensional space with reasonable confidence. The technique had been understood since Edwin Hubble's work in the 1920s. Hubble demonstrated that galaxies were receding from us and that the speed of recession increased with distance. This relationship, later formalized as Hubble's law, meant that redshift served as a cosmic odometer. Measure how much a galaxy's light has been stretched, and you can estimate how far away it is. The physics was straightforward. The challenge was practical. Measuring a redshift required capturing enough light from a galaxy to produce a clear spectrum, then carefully identifying the shifted spectral lines and calculating the displacement. For nearby bright galaxies, this took minutes. For faint distant ones, it could take hours on a large telescope. Measuring redshifts for thousands of galaxies was a monumental undertaking in the era before digital detectors and automated instruments. But by the mid-1970s, technology had advanced just enough to make systematic redshift surveys feasible. Photographic plates gave way to electronic detectors. Computers could process spectral data faster than human analysts. Telescopes could be scheduled for long survey campaigns rather than ad hoc observations. The stage was set for the first serious attempt to map the three-dimensional distribution of galaxies. In 1977, astronomers at the Harvard-Smithsonian Center for Astrophysics launched what became known as the CFA Redshift Survey. The project was modest by modern standards. Researchers measured redshifts for approximately 2,400 galaxies in a strip of sky, recording each galaxy's angular position on the sky and its redshift-derived distance. When plotted together, these coordinates placed every galaxy in a three-dimensional map. The team expected to see a roughly uniform distribution, galaxies sprinkled more or less evenly through the surveyed volume, perhaps with some mild clustering around known galaxy groups and a gentle thinning in the spaces between them. What they found instead was a revelation. The galaxies were not evenly distributed, not even close. They concentrated along thin sheets and elongated chains, separated by enormous regions containing almost nothing. The cosmic soup was not smooth at all. It had texture, architecture, a skeletal framework of matter surrounding vast empty cavities. The contrast between dense and sparse regions was not subtle, it was dramatic. Dense walls of galaxies only a few million light-years thick stretched across hundreds of millions of light-years, while the voids between them yawned open for hundreds of millions of light-years in every direction. The universe had bones. It had structure on scales nobody had anticipated. The first CFA survey hinted at this architecture. The second survey, begun in 1985, under the leadership of Margaret Geller and John Huchra, confirmed it beyond any doubt. Geller and Huchra expanded the original survey, mapping a wider and deeper slice of the universe spanning about 600 million light-years. The resulting image became one of the most famous diagrams in the history of astronomy. It was often called the Stickman diagram because of its vaguely humanoid outline, but its scientific significance dwarfed any visual resemblance to a human figure. It looked nothing like the smooth distribution that cosmology demanded. Instead, galaxies traced out a pattern of arcs, bubbles, and filamentary chains, walls of matter curved around enormous empty regions. Dense concentrations appeared at the intersections where walls met, while the interiors of the bounded regions held almost nothing. Geller described the pattern as resembling soap foam, with galaxies concentrating on the surfaces of bubbles and voids occupying the interiors. The analogy was strikingly apt. If you blew a cluster of soap bubbles and looked at where the liquid concentrated, you would see thin films at the boundaries, thicker ridges where multiple films met, and empty air inside each bubble. The galaxy distribution looked eerily similar, but the bubbles were hundreds of millions of light-years across, and the films were made of galaxies containing hundreds of billions of stars each. The most striking feature in the CFA2 survey was a vast concentration of galaxies stretching across the entire width of the mapped region. This structure, later named the CFA2 Great Wall or the Coma Wall, extended approximately 500 million light-years in length, while measuring only about 15 million light-years thick. It was enormous, spanning a significant fraction of the survey volume, and it appeared to continue beyond the survey boundaries in at least two directions. hinting that the true structure might be even larger than what the survey could see. But it was not a single gravitationally bound object. No force held the coma wall together as a coherent entity the way gravity holds a galaxy cluster together. Rather, it was a statistical pattern, a region where galaxy density was significantly higher than average, visible only when thousands of galaxy positions were plotted simultaneously. No individual galaxy within the wall felt a gravitational connection to galaxies at the opposite end. They were simply part of the same large-scale pattern in the distribution of matter, like villages that happen to line a river valley without being connected by any force other than geography. This distinction between a pattern in galaxy distribution and a physically connected object became absolutely central to the entire field. When astronomers talk about cosmic walls, filaments, and superclusters, they are describing regions where galaxies are statistically more concentrated than the cosmic average. These are not solid objects with defined surfaces. They are overdensities, zones where the probability of finding a galaxy is higher than the mean. You cannot point to a sharp edge where a filament ends and a void begins. The transition is gradual, a slow decline in galaxy density over millions of light years, like the boundary between a city and its surrounding countryside. Buildings thin out slowly. There is no wall marking where urban ends and rural starts. At some point you realize you are in farmland, but you cannot identify the precise moment you left the city. This statistical nature makes large-scale structures fundamentally different from the objects most people associate with astronomy. A star is a discrete physical thing. A planet orbits it. A galaxy cluster is gravitationally bound, its member galaxies orbiting a common center of mass, held together by the combined gravity of visible matter, hot intergalactic gas, and dark matter. A cluster is a real physical system, in the same sense that a solar system is a real physical system. You could define its membership. You could calculate its total mass. You could predict its future evolution. But a cosmic wall is more like a weather pattern. It is a region where conditions differ from the average, detectable through measurement and statistics, but not an object you could orbit around or crash into. It does not have a gravitational center. It does not rotate. Its constituents are not bound to it. Individual galaxies within a wall are bound to their local cluster, but that cluster is not bound to clusters at the other end of the wall. The wall exists only as a description of where galaxies happen to be denser than average at this particular moment in cosmic history. Over billions of years, cosmic expansion will stretch it, disperse it, and eventually erase it. The wall is a snapshot, not a permanent fixture. Understanding this distinction is essential for everything that follows. The largest structures in the universe are not objects. They are patterns, and patterns can be much larger than any object because they do not require physical forces to hold them together. They only require that the initial conditions of the universe produce density variations on correspondingly large scales. This is why the search for the largest structures in the cosmos ultimately leads back to the very beginning of time, to the quantum fluctuations that imprinted the first patterns on the fabric of reality. Around the same time that Geller and Hucre were mapping the Coma Wall, another discovery underscored just how dramatic the cosmic architecture could be. In 1981, Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman identified the Bootes Void, a roughly spherical region approximately 330 million light-years across containing remarkably few galaxies. At the time of its discovery, it was the largest known void, an immense bubble of near emptiness carved into the galaxy distribution. Its existence stunned theorists. How could such an enormous volume be so thoroughly emptied of galaxies, while surrounding regions maintained perfectly normal density? The contrast was stark. Step outside the Bootes Void in any direction, and you encounter typical cosmic web architecture, clusters, groups, filaments, the usual bustling neighborhoods of galactic civilization. Step inside and you enter a desert, not absolute emptiness, but a desolation so extreme it challenges intuition. The Bootes Void was not perfectly empty. Subsequent surveys found approximately 60 galaxies scattered through its interior, making it severely underdense rather than truly vacant. But 60 galaxies in a volume spanning 330 million light-years was shockingly sparse. The cosmic average would predict thousands of galaxies in the same volume, possibly tens of thousands depending on how deep you survey. The void contained roughly 2% of the expected galaxy population. 98% of the galaxies that should have been there, based on the cosmic mean density, were simply absent. The void's existence demonstrated something profound about the universe's matter distribution. It was far more extreme than simple models predicted. The cosmos was not gently undulating between slightly denser and slightly sparser regions. It was violently structured, with vast regions of space almost entirely devoid of luminous galaxies, existing right next to regions where matter packed into thin sheets and filaments, containing thousands of galaxies per unit volume. The dynamic range of cosmic density was enormous. From the heart of a rich galaxy cluster to the center of the Bootes void, the density of luminous matter varied by factors of hundreds or more. These discoveries, the Coma Wall, the Bootes void, and the foam-like distribution revealed by redshift surveys, launched an entirely new branch of astronomy dedicated to mapping the large-scale structure of the universe. The term cosmic web emerged in the 1990s to describe the overall architecture, popularized by cosmologists who recognized that the pattern of filaments, walls, and voids resembled a three-dimensional spider web, more than any other familiar structure. The cosmic web consists of 4 distinct components working together across the observable universe. Nodes are the densest concentrations, the massive galaxy clusters and superclusters that sit at the intersections where multiple filaments converge. These nodes are the cosmic web's cities, the bright, crowded, energetically active regions where galaxy interactions are frequent, and hot X-ray emitting gas fills the space between cluster members. Filaments are elongated chains of galaxies connecting the nodes, stretching hundreds of millions of light-years like highways between major metropolitan areas. They channel matter from voids toward nodes, acting as the cosmic web's transportation infrastructure. Walls are broad, thin sheets of galaxies that extend across enormous areas, but remain only a few million light-years thick. They form the surfaces of the cosmic bubbles, separating adjacent voids, and voids are the vast underdense regions filling the spaces between nodes, filaments, and walls, occupying roughly 80 to 90% of the total cosmic volume, while containing only a small fraction of its mass. Together, these 4 components create a foam-like architecture that extends throughout the observable universe. And the most remarkable thing about this architecture is that it was not random. It was not a frozen accident produced by chaotic initial conditions. The cosmic web is the end product of nearly 14 billion years of gravitational sculpting, shaped by processes stretching back to the very earliest moments of the universe. How those processes worked, and why they produced this specific pattern of walls and voids, would become clear only with much deeper theoretical and observational investigation. But the pattern itself was undeniable. The universe had structure, and that structure was enormous. But the CFA surveys, as groundbreaking as they were, mapped only a tiny fraction of the observable universe. Their survey volumes extended a few hundred million light-years at most, barely scratching the cosmic surface. The observable universe spans 93 billion light-years in diameter. The CFA surveys covered a volume equivalent to peering through a keyhole and trying to describe the entire mansion beyond. They revealed the existence of structure. They proved the universe had architecture. But they could not determine how far that architecture extended. Did the cosmic web continue at larger scales, or did it eventually smooth out into the uniform distribution the cosmological principle demanded? This was not an academic question. The cosmological principle is not a philosophical preference. It is the mathematical foundation upon which the entire standard model of cosmology rests. The Friedmann equations, which describe how the universe expands, are derived by assuming that matter is distributed homogeneously and isotropically at sufficiently large scales. If that assumption fails, if the universe contains structures so large that no averaging scale produces uniformity, then those equations may not apply as written. The standard model of cosmology, including our understanding of dark energy, dark matter, and the expansion history of the universe, would require revision. The stakes could not have been higher. Answering the question required measuring redshifts for not thousands, but hundreds of thousands, eventually millions, of galaxies. Surveys needed to probe billions of light-years deep, covering enough volume to determine whether the cosmic web smoothed out at some characteristic scale or continued building toward ever larger structures. The technology to attempt this was maturing rapidly. Digital detectors were becoming more sensitive. Fiber optic spectrographs could measure hundreds of galaxy redshifts simultaneously. Dedicated survey telescopes could spend years methodically sweeping across the sky, building up three-dimensional maps of unprecedented depth and breadth. By the late 1990s, two transformative projects were underway. The 2-degree Field Galaxy Redshift Survey, operating from the Anglo-Australian Telescope in Australia, began measuring redshifts for hundreds of thousands of galaxies in the southern sky. The Sloan Digital Sky Survey, using a dedicated telescope in New Mexico, launched an even more ambitious campaign to map 1/4 of the entire celestial sphere with precise redshift measurements for nearly 1 million galaxies. These surveys would map the cosmic web across billions of light years, revealing structures that made the Coma Wall look like a minor local feature. The stage was set for discoveries that would challenge the most fundamental assumptions in cosmology. Astronomers were about to learn that the cosmic web did not fade into uniformity at larger scales. It was building towards something much bigger, and the structures waiting in those deeper maps were so large that some of them threatened to break the cosmological principle entirely. What came next rewrote the scale of cosmic architecture and ignited a controversy that has not been settled to this day. The revolution arrived with a telescope in New Mexico and a plan to measure the positions of 1 million galaxies. The Sloan Digital Sky Survey, which began collecting data in the year 2000, was the most ambitious cosmic mapping project ever attempted. Using a dedicated 2.5-meter telescope at Apache Point Observatory, high in the Sacramento Mountains, the survey systematically photographed 1/4 of the entire sky using a camera containing 30 charge-coupled devices arranged in a mosaic. Each night, the telescope drifted along carefully planned strips of sky, recording the positions, brightnesses, and colors of every object it detected. Over the course of years, it catalogued hundreds of millions of celestial objects, from nearby asteroids to the most distant quasars. But the photographs were only the beginning. The survey's true power came from its spectrographs, instruments that split galaxy light into its component wavelengths and measured the characteristic spectral lines that reveal redshift. Fiber optic cables, 640 of them, plugged into custom-drilled aluminum plates, carried light from individual galaxies to the spectrographs simultaneously. Each plate was machined for a specific patch of sky, with holes drilled at the precise locations of target galaxies. Technicians plugged fibers into each hole by hand, a painstaking process repeated night after night for years. The result was an industrial-scale redshift machine capable of measuring distances to 640 galaxies in a single observation. By the time the survey reached maturity, it had measured precise redshifts for more than 900,000 galaxies. Each redshift provided a distance. Each distance placed a galaxy in three-dimensional space. When the data was assembled into maps, astronomers could fly through a virtual universe stretching billions of light years in every direction. The experience was transformative. For the first time, humanity possessed a detailed three-dimensional atlas of a significant fraction of the observable cosmos. The maps that emerged were breathtaking. Filaments twisted through space like the strands of an immense web. Dense knots of galaxies marked the intersections where filaments met, blazing with concentrated mass. Voids appeared as dark bubbles, some stretching 500 million light-years or more across, their interiors eerily sparse. Thin walls of galaxies partitioned the voids into distinct chambers, each hundreds of millions of light-years across. The pattern was consistent at every distance the survey probed. Near and far, the architecture repeated. The cosmic web was not a local anomaly confined to our immediate neighborhood. It was universal, extending as far as the survey could see. The sheer volume of data was staggering. Previous surveys had mapped thousands of galaxies across hundreds of millions of light-years. Sloan mapped hundreds of thousands across billions of light-years. The jump in scale was comparable to going from a hand-drawn sketch of your neighborhood to a satellite photograph of an entire continent. Details that had been invisible at smaller scales suddenly leaped into focus. Structures that had been hinted at by earlier surveys were now revealed in their full extent, and patterns that nobody had anticipated emerged from the data, like shapes materializing in fog. But mapping galaxies was only half the challenge. The other half was figuring out which patterns in the data were real structures and which were statistical noise. This problem is more subtle and more dangerous than it might seem. When you plot hundreds of thousands of dots in three-dimensional space, the human eye will find patterns everywhere. Lines, clusters, rings, arcs, chains. The brain is a pattern recognition engine of extraordinary power, honed by millions of years of evolution. Our ancestors survived by spotting predators hiding in foliage, identifying edible plants among toxic lookalikes, and recognizing faces in dim firelight. The neural circuitry that made those feats possible is the same circuitry that now analyzes galaxy maps, and it does not switch off just because the stakes have changed from survival to science. It sees patterns whether they exist or not. This tendency, sometimes called apophenia, has generated some of astronomy's most embarrassing moments. Percival Lowell convinced himself he could see canals on Mars, engineered waterways built by an intelligent civilization. He was seeing patterns in blurry telescope images that simply were not there. The history of science is littered with similar examples, researchers finding exactly the structure they expected in noisy data because their brains were primed to detect it. In cosmology, the risk is magnified by the sheer complexity of the datasets. A three-dimensional galaxy map containing hundreds of thousands of points offers essentially unlimited opportunities for pattern detection. You could find walls, rings, spirals, letters of the alphabet, anything your visual cortex decides to assemble from the dots. To combat this, astronomers developed rigorous statistical tools for identifying genuine concentrations in galaxy distribution data. These tools do not rely on visual inspection. They use mathematical algorithms to compare the observed distribution of galaxies against what you would expect from a completely random arrangement. If the observed data shows statistically significant deviations from randomness, those deviations represent real structure. If they do not, the apparent patterns are noise. The most fundamental of these tools is the two-point correlation function. The concept is straightforward. Pick any galaxy in the survey. Count how many other galaxies lie within a given distance of it. Compare that count to the number you would expect if galaxies were distributed randomly at the same average density. If you find more galaxies than random chance predicts, the excess measures the strength of clustering at that scale. Repeat the calculation for every galaxy in the survey and average the results. The two-point correlation function summarizes how galaxy clustering strength varies with distance, providing a statistical fingerprint of the cosmic web's architecture. The results from the Sloan Digital Sky Survey confirmed what the maps showed visually, but with mathematical precision that visual inspection could never achieve. Galaxies are strongly clustered at scales up to about 30 million light-years, the typical size of galaxy groups and small clusters. Clustering remains significant but weaker out to about 300 million light-years, the scale of superclusters and the largest filaments. Beyond roughly 1 billion light-years, the correlation function approaches zero, meaning that galaxies at those separations are distributed almost randomly relative to each other. This transition scale became one of the most important numbers in cosmology. It represents the distance above which the universe begins to look statistically uniform, the scale at which the cosmological principle kicks in. Below this scale, the cosmos is lumpy, organized into the intricate web of filaments, walls, and voids. Above this scale, the lumpiness averages out. Look at a volume larger than roughly 1 to 1.3 billion light-years on a side, and you see approximately the same density of galaxies, regardless of where in the observable universe you look. The cosmological principle demands that such a transition exist. If galaxy distribution never becomes uniform at any scale, if the universe remains structured all the way up to the largest observable distances, then the foundational assumption of modern cosmology fails. The Friedmann equations that describe cosmic expansion assume homogeneity. Models of dark energy, dark matter, and the Big Bang all rest on this assumption. If the universe is not homogeneous at sufficiently large scales, those models require modification or replacement. The transition to homogeneity is therefore not just a statistical curiosity, it is the empirical foundation upon which the entire edifice of modern cosmology stands. The measured homogeneity scale of roughly 300 to 400 megaparsecs, which translates to approximately 1 to 1.3 billion light-years, set a theoretical ceiling for how large a coherent structure could be. Any structure larger than this scale would, in principle, violate the cosmological principle. If you could point to a region of the universe 1.5 billion light-years across that was significantly denser or emptier than average, it would represent a deviation from homogeneity at a scale where homogeneity is supposed to hold. The CFA2 Great Wall, at 500 million light-years, sat comfortably below this ceiling. Even the largest filaments and voids revealed by early surveys respected the threshold. The cosmological principle appeared safe. The universe had structure, but the structure had limits. The ceiling was there, clearly defined, apparently firm, and researchers were about to find structures that crashed through it. Before reaching those controversial giants, though, the Sloan Digital Sky Survey delivered one of the most impressive confirmed structures in the cosmic web. In 2003, Richard Gott and colleagues at Princeton University announced the discovery of the Sloan Great Wall, a vast concentration of galaxies extending approximately 1.37 billion light-years in length. This was not a modest incremental increase over previous records. The Sloan Great Wall was roughly 3 times longer than the CFA2 Great Wall. It was among the largest recognized structures in the observable universe at the time, a chain of galaxy clusters and superclusters stretching across more than 1% of the diameter of the observable cosmos. The Sloan Great Wall sits at a distance of roughly 1 billion light-years from Earth, placing it well within the survey's high-quality mapping volume. It was identified by tracing overdense regions in the 3-dimensional galaxy distribution, linking together multiple galaxy clusters and superclusters that formed a nearly continuous chain of above-average density. The overdensity was not dramatic at any single point. No individual location within the wall showed galaxy concentrations vastly exceeding typical cluster densities. Rather, the wall revealed itself as a coherent pattern of modest overdensity extending over an enormous length, visible only when the survey's full 3-dimensional dataset was analysed statistically. The wall's length placed it right at the homogeneity scale. At 1.37 billion light-years, it brushed against the theoretical ceiling, but did not unambiguously breach it. Defenders of the cosmological principle could argue that the Sloan Great Wall represented an expected extreme, a statistical fluctuation at the tail end of the probability distribution, rare but not impossible within a homogeneous universe. Structures near the homogeneity scale are predicted to exist occasionally, just as unusually tall or short people exist within a population that has a well-defined average height. The Sloan Great Wall was an outlier, not a violation. But its discovery raised an uncomfortable question. If the largest survey yet conducted found a structure right at the theoretical limit, what would even larger surveys find? Were there walls and filaments stretching 2 billion light-years? 5 billion? 10? Each improvement in survey depth and breadth risked discovering structures that could no longer be dismissed as statistical outliers. The distinction between gravitationally bound and statistically identified structures deserves particular emphasis here, because it is central to understanding what astronomers mean when they discuss the largest structures in the universe. The Coma cluster, which sits within the Sloan Great Wall, is gravitationally bound. Its more than 1,000 member galaxies orbit within a shared dark matter halo. Gravity holds the cluster together against the expansion of space. The Coma cluster will persist as a coherent system for billions of years, its galaxies circling their common center of mass like a swarm of bees around a hive. The Sloan Great Wall, like the Coma Wall before it, is not a gravitationally bound object. Cosmic expansion is actively stretching the distances between its constituent clusters. The clusters at opposite ends are being carried apart by expanding space. Over billions of years, expansion will disperse it. The wall is a snapshot of the galaxy distribution at a particular moment in cosmic time, not a permanent feature. Superclusters occupy a similar conceptual space between bound objects and statistical patterns, but a landmark discovery in 2014 revealed just how much more nuanced the picture could be. Brent Tully and colleagues, working with data from the Cosmic Flows project, identified what they named the Laniakea supercluster, a vast cosmic basin spanning approximately 520 million light-years and containing roughly 100,000 galaxies, including our own Milky Way. What made Tully's work revolutionary was not the identification of a large supercluster. Astronomers had recognized that our galaxy belonged to a broader superstructure since the 1950s, when George de Vaucouleurs proposed the local supercluster. What was revolutionary was the method. Rather than defining Laniakea by galaxy density, which would have produced ambiguous boundaries that shifted depending on the density threshold chosen, Tully's team mapped the peculiar velocity flows of thousands of galaxies throughout the local universe. Peculiar velocities are the motions galaxies exhibit on top of the overall cosmic expansion. Every galaxy participates in the Hubble flow, the uniform recession caused by expanding space. But galaxies also feel gravitational pulls from nearby concentrations of matter, which add additional velocity components directed toward those concentrations. These extra motions are typically modest, a few hundred kilometers per second compared to the tens of thousands, characterizing the Hubble flow at cosmological distances. But they are measurable using distance indicators independent of redshift, such as the Tully-Fisher relation, which links a spiral galaxy's rotation speed to its intrinsic luminosity. By painstakingly measuring these peculiar velocities for more than 8,000 galaxies, Tully's team could reconstruct the gravitational landscape of the local cosmos. They mapped the flow field, the pattern of streaming motions showing where galaxies were being pulled and by what. The picture that emerged was of a vast gravitational watershed. Galaxies throughout a region spanning 520 million light-years were streaming toward a common basin centered on the Great Attractor, a massive concentration of matter lying approximately 200 million light-years away in the direction of the constellations Centaurus and Norma, partially hidden behind the Milky Way's own dust-filled disk. The supercluster's boundary was defined as the surface where these flows diverged, where galaxies stopped falling toward the Great Attractor and began falling toward neighboring gravitational basins. It was the cosmic equivalent of a continental divide, the ridgelines separating rivers that drain to different oceans. On one side, galaxies flow toward the Great Attractor and belong to Laniakea. On the other side, they flow toward the Shapley supercluster or the Perseus-Pisces chain and belong to different superclusters entirely. The boundary was not a wall or a density threshold. It was a dynamical surface defined by motion rather than position. But even Laniakea is not fully gravitationally bound. Dark energy is accelerating the expansion of space throughout the supercluster's volume. Its outermost regions, where gravitational attraction toward the Great Attractor is weakest and expansion most dominant, will eventually be torn away. Some galaxies currently counted as Laniakea members will drain into the Shapley Basin. Others will be carried into expanding voids. The supercluster is a transient feature, a cosmic watershed that will persist in its current form for perhaps a few billion years before dark energy disrupts it. Like the Great Walls, it is a pattern in the present distribution of matter, not a permanent gravitational structure. The 2-degree field galaxy redshift survey, commonly abbreviated as 2DFGRS, complemented the Sloan survey by mapping galaxies across a different portion of the sky. Operating from the Anglo-Australian telescope at Siding Spring Observatory in New South Wales, the survey measured redshifts for approximately 220,000 galaxies using a robotic fiber positioner that could place 400 fibers on target galaxies simultaneously. Completed in 2003, it produced an independent 3-dimensional galaxy map that revealed the same cosmic web architecture seen by Sloan. The consistency between these two surveys, conducted by different teams using different telescopes, different instruments, different software pipelines, and different patches of sky, was a powerful confirmation that the observed structures were real. The cosmic web was not an artifact of the Sloan telescope's optics, or the team's analysis software, or a peculiarity of the northern sky. It appeared identically in independent data from the southern hemisphere. The architecture was genuine. Buried within these massive datasets was a subtle signal that would become one of cosmology's most indispensable tools. Baryon acoustic oscillations are frozen relics of sound waves that rippled through the hot plasma of the early universe. The physics behind them reaches back to the first few 100,000 years after the Big Bang, when the universe was a dense, opaque fog of protons, electrons, and photons, a seething plasma so hot and pressurized that it behaved more like a fluid than a gas. In this primordial fluid, two forces waged a constant battle. Gravity pulled baryonic matter toward concentrations of dark matter, attempting to build the first overdensities. But radiation pressure, the outward push of photons trapped in the plasma, resisted the collapse. The result was not stalemate but oscillation. Matter fell inward, compressed, and then bounced outward as photon pressure overwhelmed gravity, only to fall inward again as gravity reasserted itself. These oscillations were, in the most literal sense, sound waves. They were compressions and rarefactions propagating through a medium, identical in principle to the sound waves that carry music through air, but operating at cosmic scales in a fluid denser and hotter than the interior of any star. Each initial dark matter overdensity launched a spherical sound wave that propagated outward through the plasma at approximately half the speed of light. The wave carried baryonic matter with it, creating a shell of slightly enhanced density expanding outward from the original dark matter concentration. Multiple waves from countless overdensities overlapped and interfered, filling the universe with a complex pattern of compressions and rarefactions. This acoustic activity continued until the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, approximately 380,000 years after the Big Bang. At that moment, the photons that had been providing radiation pressure decoupled from the baryonic matter and streamed freely through space, eventually becoming the cosmic microwave background radiation we detect today. With the photons gone, the pressure vanished. The sound waves froze in place. Each spherical wave stopped expanding at exactly the distance it had travelled since the Big Bang, roughly 490 million light-years in today's expanded coordinates. This distance was imprinted permanently into the distribution of matter as a slight excess of baryonic material at that specific radius from every initial overdensity. The frozen scale shows up as a subtle statistical excess in the probability of finding two galaxies separated by approximately 490 million light-years, compared to slightly smaller or slightly larger separations. The signal is not dramatic. It represents a bump of only a few % above the smooth background of galaxy clustering statistics. You would never notice it by looking at a galaxy map. It reveals itself only through careful statistical analysis of enormous datasets containing hundreds of thousands of galaxy positions. But the bump is there, reproducible across independent surveys, and it provides one of the most precise measuring tools available to cosmologists. Because the physics that produce this scale is thoroughly understood, From the composition of the primordial plasma to the speed of sound within it, to the precise moment when atoms formed, astronomers can calculate exactly how large the baryon acoustic oscillation scale should be at any given cosmic epoch. Comparing the predicted physical size to the observed apparent size at different redshifts reveals how much the universe has expanded between then and now. This comparison, repeated at multiple distances, traces the expansion history of the universe with remarkable precision, constraining the properties of dark energy and the overall geometry of space. The Baryon Oscillation Spectroscopic Survey, known as BOSS, was specifically designed to exploit this cosmic ruler to its fullest potential, operating from 2009 to 2014 as part of the third phase of the Sloan Digital Sky Survey. BOSS measured redshifts for approximately 1.5 million luminous red galaxies and over 160,000 quasars. These targets were chosen because they are bright enough to be detected at great distances, allowing the survey to map galaxy positions across a volume spanning several billion light-years in each direction. The resulting three-dimensional maps covered a cosmic volume roughly 10 times larger than the original Sloan survey. The baryon acoustic oscillation measurements from BOSS achieved percent-level precision in constraining the expansion rate of the universe at multiple cosmic epochs. This precision, combined with independent measurements from the cosmic microwave background and distant supernovae, tightened the constraints on dark energy properties and confirmed that cosmic expansion has been accelerating for the past 5 billion years or so. The ruler worked exactly as predicted, but BOSS also revealed new large-scale structures. In 2016, a team of researchers announced the discovery of the BOSS Great Wall, a massive complex of superclusters stretching approximately 1 billion light-years across. Like the walls before it was identified through overdensity in the galaxy distribution rather than any shared gravitational binding. The accumulating catalogue of Great Walls told a consistent story. The CFA 2 Great Wall at 500 million light-years, the Sloan Great Wall at 1.37 billion light-years, the BOSS Great Wall at approximately 1 billion light-years. All of these structures sat at or just below the theoretical homogeneity scale. They were enormous, among the largest confirmed features in the observable universe, but they did not flagrantly violate the cosmological principle. They represented the expected extremes of cosmic web architecture, the largest patterns that gravitational physics should produce given the initial density fluctuations imprinted by inflation. Simulations of cosmic structure formation using the standard cosmological model occasionally generated comparable features, confirming that walls of this size were rare but not theoretically impossible. The cosmological principle appeared to be holding. The universe had structure, dramatic structure on scales that would have astonished astronomers just decades earlier. But that structure seemed to respect a maximum scale. Above roughly 1.3 billion light-years, the galaxy distribution trended toward uniformity. The cosmic web was magnificent, but bounded. The architecture had a ceiling. Then, other detection methods began probing scales that galaxy redshift surveys had not yet reached. Instead of mapping the positions of ordinary galaxies, some research teams turned to more exotic cosmic beacons. Quasars, the brilliantly luminous nuclei of distant galaxies powered by supermassive black holes consuming matter at prodigious rates, can be detected across most of the observable universe. A single quasar can outshine its entire host galaxy by factors of hundreds, making it visible at distances where ordinary galaxies fade below detection thresholds. Gamma-ray bursts, the most energetic explosions in the cosmos, produce brief flashes of radiation detectable from even greater distances. These objects offered a tantalizing possibility. If quasars and gamma-ray bursts trace the underlying distribution of matter, then clustering in their positions could reveal large-scale structure at distances and scales inaccessible to ordinary galaxy surveys. A group of quasars concentrated in a particular region of sky at a particular redshift might indicate an enormous overdensity of matter at that location, a structure far too distant for galaxy surveys to have mapped directly. The method was promising but fraught with complications. Quasars and gamma-ray bursts are far rarer than ordinary galaxies. A survey that finds millions of galaxies might detect only thousands of quasars and hundreds of gamma-ray bursts. Smaller samples mean weaker statistical power. Patterns that would be obvious in a million-galaxy dataset might be ambiguous or invisible in a few hundred burst catalogue. The risk of mistaking random clustering for genuine structure increases dramatically as sample sizes decrease. Furthermore, the relationship between these exotic objects and the underlying matter distribution is not straightforward. Quasars are associated with supermassive black holes in a particular phase of active growth, which depends on factors like gas supply, galaxy mergers, and local environment. They are not simple tracers of total mass. A concentration of quasars might indicate a concentration of matter, or it might indicate a region where conditions happen to trigger more black hole activity without any unusual total mass. Gamma-ray bursts are associated with the deaths of massive stars or the mergers of compact objects, processes that depend on star formation history and stellar evolution rather than directly on large-scale matter density. Despite these caveats, several research teams pushed ahead. They applied clustering algorithms to quasar catalogues and gamma-ray burst databases, searching for concentrations spanning scales far larger than any galaxy wall. When they found apparent structures stretching billions of light-years across, the scientific community fractured. Some researchers celebrated the discoveries as revolutionary evidence that the universe contains structures vastly exceeding the homogeneity scale. Others dismissed them as statistical illusions, artifacts of small sample sizes, flawed detection algorithms, and the human brain's relentless tendency to find patterns in noise. The controversy struck at the heart of cosmology's most basic assumptions. The structures that sparked this battle were so large, they made the Sloan Great Wall look like a single brick in a cosmic cathedral. If real, they would mean that the universe is far less uniform at the largest scales than the standard model of cosmology can explain. If illusory, they would demonstrate the dangers of drawing cosmic conclusions from sparse datasets. Either way, the debate forced astronomers to confront a question they had assumed was settled. How large can structures in the universe actually get? The answer waiting in the data was more extreme than almost anyone had predicted, and the arguments it ignited have not been settled to this day. In January of 2013, a team led by Roger Clowes at the University of Central Lancashire published a paper that sent tremors through the cosmological community. They had been analysing the spatial distribution of quasars in a catalogue compiled from the Sloan Digital Sky Survey, searching for clustering patterns at extreme cosmic distances. What they found was a group of 73 quasars concentrated in a region of space approximately 4 billion light-years across, sitting at a distance of roughly 9 billion light-years from Earth. They named it the Huge Large Quasar Group, or Huge LQG. If it was a genuine structure, it was the largest thing anyone had ever identified in the observable universe, and it was not supposed to exist. Quasars are the intensely luminous cores of distant galaxies powered by supermassive black holes consuming vast quantities of infalling matter. As gas spirals inward toward the black hole, friction heats it to temperatures of millions of degrees, producing radiation across the entire electromagnetic spectrum. A single quasar can outshine its entire host galaxy by factors of 100 or more, blazing with the luminosity of 1 trillion suns packed into a volume smaller than our solar system. This extraordinary brightness makes quasars visible at distances where ordinary galaxies fade below detection thresholds, turning them into beacons that mark the positions of massive galaxies across most of the observable universe. Astronomers had known for decades that quasars were not randomly scattered through space. They tended to cluster together, forming groups that traced the underlying cosmic web at distances too great for ordinary galaxy surveys to reach. Large quasar groups had been catalogued since the 1980s. Most measured a few 100 million light-years across, consistent with known supercluster scales. They were interesting but unremarkable, simply the quasar-traced equivalents of the galaxy walls and filaments already mapped in the nearer universe. The huge LQG dwarfed all previous examples. Its longest dimension spanned approximately 4 billion light-years, more than 3 times the theoretical homogeneity scale of roughly 1.2 billion light-years. The homogeneity scale, established by galaxy redshift surveys as the distance above which the universe appears statistically uniform, was supposed to represent a firm ceiling on structure size. A coherent concentration of matter 3 times that size did not merely push the ceiling, it demolished it. Klaus and his team identified the huge LQG using a linkage algorithm called a friends of friends method. The technique is conceptually simple, but operationally subtle. Start with one quasar. Search outward and find every other quasar within a specified linking distance. Then repeat the search from each of those newly connected quasars, finding their neighbours within the same linking distance. Continue the process iteratively until no more connections can be made. The final connected set of objects is defined as a group. The algorithm is agnostic about shape or geometry. It does not look for walls or filaments or spheres. It simply connects nearby objects into clusters, letting the data determine the resulting structure's form. The choice of linking distance is the algorithm's most consequential parameter. Set the linking distance too large, and you will connect nearly everything into one enormous artificial supergroup. The algorithm will bridge gaps that represent genuine empty space, chaining together unrelated clumps into a single monstrous artifact. Set it too small and you will fragment real structures into disconnected pieces, breaking continuous filaments into isolated nuggets that lose their collective significance. The linking distance must be calibrated to the average spacing between objects at that cosmic epoch, so that it connects genuinely associated members without bridging unrelated populations. Klaus used a linking distance based on the mean separation of quasars at the relevant redshift, a standard and well-justified choice. The resulting group contained 73 quasars spanning 4 billion light-years. The team tested the result against random simulations, generating thousands of mock quasar catalogues with the same average density but no built-in structure. They found that random catalogues rarely produced groups this large, suggesting the huge LQG was unlikely to be a chance alignment. The reaction from the broader community was immediate and fierce. Critics raised several objections, each targeting a different vulnerability of the detection method. The first objection concerned the sensitivity of friends algorithms to their linking parameter. Even small changes to the linking distance can produce dramatically different results. Increase it by 10%, and previously separate groups merge into one. Decrease it by 10%, and a single massive group fractures into several smaller ones. Critics argued that the huge LQG might not be a single coherent structure at all, but rather a chain of smaller unrelated quasar groups that the algorithm happened to connect through a few bridging members. Think of it like a chain of islands. Each island is real, but the chain connecting them into a single archipelago depends on where you draw the linking threshold. Lower the sea level slightly, and previously separate islands merge into a single landmass. Raise it slightly, and the archipelago splits into isolated rocks. The huge LQG might be the cosmological equivalent of a low-tide illusion, separate islands temporarily connected by an algorithmic choice. The second objection was statistical. When researchers generated random quasar distributions matching the observed density and applied the same friends of friends algorithm, they occasionally produced groups of comparable size purely by chance. The probability was low, but not negligible. Some analyses placed it around 2 to 5%, meaning that in a universe fully consistent with the cosmological principle, you would expect to find a structure resembling the huge LQG once or twice across the observable volume without invoking any new physics. A 2% probability sounds impressively small in everyday life. In cosmology, where the observable universe offers an enormous volume in which rare events can occur, it is not small enough to be conclusive. The third objection targeted the relationship between quasars and total matter distribution. Quasars are not passive tracers of mass. They are active galactic nuclei in a specific evolutionary phase, requiring particular conditions to ignite, including sufficient gas supply, recent galaxy mergers, or specific environmental triggers. A concentration of quasars does not necessarily indicate a concentration of total matter. It could instead reflect a region where conditions happen to trigger more black hole activity, perhaps due to an elevated merger rate or an unusually gas-rich environment, without any exceptional total mass. If the huge LQG marks a region of enhanced quasar activity rather than enhanced matter density, it might not represent a large-scale structure in the physical sense at all. Supporters of the discovery pushed back on each point. They argued that the huge LQG was not merely elongated in one dimension like a fragile chain, but showed genuine three-dimensional overdensity compared to surrounding regions. The quasar concentration exceeded the cosmic mean density in that volume by a statistically significant margin, regardless of the specific algorithm used to define its boundaries. Alternative statistical measures beyond friends of friends, including nearest neighbor analyses and density field reconstructions, confirmed the overdensity. Something physically meaningful existed in that region of space, even if its precise boundaries were debatable. The debate reached no consensus. Papers arguing for and against the huge LQG continued to appear for years, each bringing new statistical tests and new counterarguments. The structure occupied an uncomfortable middle ground, too significant to dismiss casually, but too ambiguous to accept confidently. It sat in the scientific literature like an unresolved court case, evidence presented by both sides, verdict pending. But while cosmologists argued over the huge LQG, an even more provocative candidate emerged from an entirely different type of data. In 2015, Lajos Balázs and an international team of researchers announced the discovery of a ring-shaped concentration of gamma-ray bursts at a distance of approximately 7 billion light-years from Earth. The detection came not from galaxy surveys or quasar catalogues, but from databases maintained by space-based gamma-ray observatories, satellites designed to detect the brief, violent flashes of high-energy radiation produced by the most catastrophic events in the cosmos. Gamma-ray bursts come in two main varieties. Long-duration bursts, lasting more than 2 seconds, are typically produced when massive stars exhaust their nuclear fuel and collapse into black holes, launching relativistic jets that punch through the dying star's outer layers. Short-duration bursts, lasting less than 2 seconds, are generally attributed to the merger of compact objects like neutron star pairs. Both types release more energy in seconds than the Sun will produce in its entire 10 billion year lifetime. This extraordinary output makes them detectable at cosmological distances, providing markers of cosmic activity at epochs when the universe was less than half its current age. The giant gamma-ray burst ring, as the discovery became known, consisted of 9 gamma-ray bursts arranged in a rough circular pattern, approximately 5.6 billion light-years in diameter. The bursts occurred at similar redshifts, placing them at comparable distances from Earth and suggesting they occupied a coherent shell or ring of space rather than being scattered randomly along the line of sight. Balázs and colleagues calculated the probability of 9 bursts arranging themselves into this pattern by random chance. Their analysis returned a probability of less than 1 in 20,000, a figure that seemed to rule out coincidence. If the giant GRB ring traced a genuine underlying structure, the implications were extraordinary. At 5.6 billion light-years across, it would exceed the homogeneity scale by a factor of nearly 5. No known physical mechanism could create a ring of enhanced galaxy density at that scale. The baryon acoustic oscillation imprint, the most prominent known feature in the matter distribution, produces a characteristic scale of roughly 490 million light-years, more than 10 times smaller than the ring. Gravitational collapse, even operating over the full age of the universe, cannot organize matter into coherent patterns spanning billions of light-years. The forces simply do not reach that far in the available time. Some researchers propose the ring might represent a cross-section through a massive spherical shell, a three-dimensional bubble of enhanced density sliced by the observer's line of sight to produce an apparent ring. Spherical shells can form through energetic processes, explosive outflows from active galactic nuclei, for instance, or the expanding remnants of primordial density perturbations. But known mechanisms produce shells measured in millions of light-years, not billions. Scaling any known process up to 5.6 billion light-years requires invoking physics for which no evidence exists. Skeptics offered a simpler explanation. 9 data points arranged in an approximate circle do not constitute robust evidence for anything. The human visual system is exceptionally good at perceiving circular patterns. Show someone 9 randomly placed dots and ask whether they see any geometric shapes. More often than not, they will find circles, arcs, triangles, or other familiar forms. This is the same pattern recognition machinery that finds faces in clouds and animals in star constellations. It is powerful, instinctive, and thoroughly unreliable when applied to small data sets. The statistical significance claimed by Balazs and colleagues depended on the specific tests applied and the assumed null hypothesis. Different analysts, using different methods, reached different conclusions about the ring's significance. Some confirmed the low probability of chance occurrence. Others found that the probability was higher than initially reported when additional statistical corrections were applied. The look elsewhere effect, the inflation of apparent significance that occurs when multiple tests are performed on the same data, remained a persistent concern. Gamma-ray bursts are also problematic tracers of large-scale structure for reasons specific to their detection. Space-based gamma-ray observatories do not survey the sky uniformly. Their sensitivity depends on the direction they are pointing at any given moment, which varies with satellite orbit, instrument configuration, and operational constraints. Some regions of the sky receive more observation time than others, creating artificial density variations in the detected burst population. Correcting for these observational selection effects requires detailed modelling of each observatory's exposure history, and subtle errors in these corrections can produce spurious clustering signals. Then came the biggest candidate of all, the one that, if confirmed, would represent the single most dramatic challenge to the cosmological principle in the history of modern astronomy. The Hercules-Corona Borealis Great Wall was first proposed in 2013 by István Horváth and collaborators at the National University of Public Service in Budapest, with follow-up analyses published in 2014 and 2015. Horváth's team studied the angular distribution and redshift properties of gamma-ray bursts detected by multiple space observatories over more than a decade, including NASA's SWIFT satellite and several earlier missions. The combined dataset contained several hundred bursts, with measured redshifts, enough to search for large-scale clustering patterns across the sky. What they found was a concentration of gamma-ray bursts in the direction of the northern constellations Hercules and Corona Borealis, at redshifts corresponding to distances of roughly 10 billion light-years from Earth. The excess was not subtle. The region contained significantly more bursts than expected based on the average sky density, even after accounting for known variations in observatory sensitivity and exposure time. Horváth's team tested the significance using multiple statistical methods and consistently found that the excess was unlikely to arise from random fluctuation in a uniform distribution. The implied scale was staggering. The region of elevated gamma-ray burst density spanned approximately 10 billion light-years across. To place that number in context, the entire observable universe measures approximately 93 billion light-years in diameter. A structure 10 billion light-years across would occupy roughly 1/9 of that full diameter. It would be approximately 7 times larger than the Sloan Great Wall, more than twice the size of the huge LQG, and nearly 8 times the theoretical homogeneity scale. If the Hercules-Corona Borealis Great Wall represented a genuine concentration of matter, it would be the largest structure ever identified by any method, by an enormous margin. The detection methodology differed fundamentally from the redshift surveys that identified confirmed structures like the Sloan Great Wall or the Boss Great Wall. Those surveys mapped individual galaxies by the hundreds of thousands, building dense, three-dimensional models of matter distribution with high statistical confidence. Every galaxy in those surveys had a precisely measured position and redshift. The resulting maps were rich enough to apply sophisticated clustering algorithms and clearly distinguish genuine structures from noise. The Hercules-Corona Borealis Great Wall was inferred indirectly from the angular clustering of gamma-ray bursts in a catalogue containing only a few hundred events with measured redshifts. The structure was not mapped galaxy by galaxy. It was identified by noticing that one patch of sky contained more gamma-ray bursts at a particular distance range than statistical uniformity would predict. The leap from excess gamma-ray bursts to excess galaxies to a coherent physical structure involved multiple assumptions, each introducing uncertainty. This indirect approach generated intense and sustained scrutiny from the cosmological community. The criticisms fell into several categories, each attacking a different link in the chain of inference. The first category concerned observational selection effects. Gamma-ray burst detection depends on instrument sensitivity, satellite pointing direction, trigger algorithms, and follow-up observation availability. A burst detected by SWIFT must be bright enough to trigger the satellite's onboard detection software, which has specific energy and flux thresholds. Fainter bursts in regions of lower sensitivity go undetected. If the sensitivity pattern of the combined observatory network happens to favor the Hercules-Corona Borealis region, it could create an apparent excess where none exists. Horvath and colleagues corrected for known exposure variations, but critics argued that more subtle instrumental effects could remain. The second category concerned the relationship between gamma-ray bursts and large-scale structure. Long-duration gamma-ray bursts trace massive star formation. Regions with more massive star formation produce more bursts, but massive star formation depends on local conditions within individual galaxies, gas supply, metallicity, merger history, rather than on the large-scale matter density averaged over billions of light-years. A region with elevated massive star formation might represent a genuine overdensity of galaxies, or it might represent a region where environmental factors happen to produce more massive stars per galaxy without any unusual total galaxy count. The connection between burst density and matter density is real but indirect, mediated by astrophysical processes that introduce scatter and systematic uncertainty. The third category was purely statistical. The look elsewhere effect haunts every search for anomalies in sparse datasets. When you examine a sky map in hundreds of different directions, at dozens of different distance ranges, using multiple statistical metrics, you are performing thousands of implicit tests. Even in perfectly uniform data, some of those tests will produce results that appear highly significant when evaluated in isolation. The question is whether the Hercules-Corona Borealis excess remains significant after accounting for all the other directions, distances and methods that were examined and found nothing unusual. Horvath's team addressed this concern in their analyses, but the appropriate correction factors remain debated. A fourth criticism targeted the very concept of a structure at this scale. Even if the gamma-ray burst excess is real and traces a genuine overdensity of galaxies, calling it a structure implies a level of physical coherence that may not exist. A region 10 billion light-years across cannot be gravitationally bound. Light itself requires 10 billion years to cross it. No causal connection, gravitational or otherwise, can link its opposite ends within the age of the universe. If it exists as an overdensity, it must reflect initial conditions imprinted during or shortly after inflation. Primordial density fluctuations on scales far larger than standard inflationary models typically produce. This does not make it impossible, but it pushes the explanation into territory where observational constraints are weakest and theoretical speculation is most uncertain. The scientific community remains deeply divided, and the nature of this division reveals something important about how science actually operates when the stakes are high and the data is ambiguous. This is not a case where one side has the evidence and the other is in denial. Both camps include accomplished scientists using legitimate methods and making defensible arguments. The disagreement reflects a genuine ambiguity in the data, an ambiguity that current observations cannot resolve. The candidate structures exist in a twilight zone between confirmed and refuted, significant enough to demand attention but not definitive enough to compel acceptance. Within this twilight zone, the debate has played out across journal pages, conference presentations, and preprint servers in a pattern familiar to anyone who studies scientific controversy. A team announces a detection. Other teams attempt to reproduce the result using different methods or different data. Some succeed, others fail. The original team publishes refinements. Critics publish rebuttals. Each new paper adjusts the statistical significance up or down by fractions that are technically meaningful but practically inconclusive. The accumulated literature grows, but the fundamental question remains open because the data itself is too sparse to answer it definitively. Conference sessions on large-scale structure have become arenas for this unresolved tension. A speaker presents evidence for the huge LQG as a genuine overdensity and receives pointed questions about linking distance sensitivity from the audience. Another speaker demonstrates that simulations can occasionally reproduce similar structures by chance, and faces equally pointed questions about whether the simulation parameters were chosen to maximize that probability. The exchanges are professionally cordial but substantively fierce. Careers and reputations are entangled with the outcome. The researchers who detected these structures face the pressure of defending discoveries that some colleagues consider artifacts. The researchers who challenged them face the risk of dismissing something that future surveys might confirm. What makes this debate particularly difficult to resolve is an asymmetry at its heart. Proving that a structure is real requires only one decisive piece of evidence, an independent detection using a completely different method. But proving that a structure is not real, that it is a statistical artifact, is far harder. You cannot prove a negative with finite data. You can only demonstrate that the data is consistent with the null hypothesis, which is not the same thing. The absence of evidence is not evidence of absence, as the saying goes, and in cosmology the absence of evidence often simply reflects the inadequacy of current surveys. Proponents of these structures argue that the detections are statistically robust, and that dismissing all three candidates, the huge LQG, the giant GRB ring, and the Hercules-Corona Borealis Great Wall, as independent artifacts requires assuming an improbable coincidence of systematic errors across multiple datasets analyzed by multiple teams using multiple methods. The clustering signals come from different object types detected by different instruments at different cosmic distances. If all three are artifacts, the artifacts must arise from different and unrelated causes, which critics would then need to identify and demonstrate individually. Critics counter that extraordinary claims require extraordinary evidence. The cosmological principle is supported by decades of precision measurements from galaxy surveys, the cosmic microwave background, and baryon acoustic oscillation analyses. Indirect detections based on small samples of rare objects do not meet the evidentiary standard required to overturn this foundation. Every candidate structure has plausible alternative explanations, from algorithmic sensitivity to observational selection effects to the look elsewhere problem. Until a candidate structure is independently confirmed through direct galaxy mapping at the relevant distance, skepticism is the scientifically appropriate response. Several explanations have been proposed to reconcile these candidate structures with existing cosmological theory if they do turn out to be real. The simplest is that the homogeneity scale has been underestimated. Perhaps the universe does not transition to statistical uniformity at 1.2 billion light-years, but at some larger scale, 5 or 6 billion light-years. This would preserve the cosmological principle in spirit, while revising the specific distance at which it applies. However, this explanation conflicts with the galaxy correlation function data, which consistently shows clustering approaching zero at scales around 300 to 400 megaparsecs. Pushing the homogeneity scale outward by a factor of 5 would require explaining why these well-established measurements are misleading, a difficult proposition given their precision and reproducibility. A more radical possibility is that the cosmological principle is wrong, or at least a rougher approximation than currently assumed. Perhaps the universe contains genuine inhomogeneities at scales of billions of light-years that the standard model simply cannot accommodate. This would have cascading consequences throughout cosmology. Distance measurements calibrated against homogeneous models would need revision. Dark energy constraints derived from baryon acoustic oscillations would shift. The interpretation of the cosmic microwave background, the linchpin of precision cosmology, might require modification. The entire framework that has successfully explained observations from the first few minutes after the Big Bang to the present day would need rebuilding. Another possibility lies in the physics of inflation. If the quantum field that drove inflation experienced fluctuations or transitions during the inflationary epoch, it could have imprinted anomalous power at very large scales, creating regions of enhanced or suppressed density far larger than the standard inflationary power spectrum predicts. These imprints would show up as structures exceeding the homogeneity scale, without violating the cosmological principle at even larger scales. The universe would still be homogeneous on average, but the average would be computed over a volume much larger than the observable universe. This explanation is theoretically elegant, but essentially untestable. If the relevant scale exceeds the observable universe, we can never confirm that homogeneity is restored at that level. The resolution will come from data, and the data is coming fast. Next-generation surveys already underway or nearing completion will map the universe with unprecedented breadth, depth, and statistical power. The Dark Energy Spectroscopic Instrument, installed at the Mayall Telescope at Kitt Peak National Observatory and in full operation since 2021, is measuring redshifts for approximately 40 million galaxies and quasars, across a volume vastly larger than any previous survey. Its 5,000 robotic fiber positioners can reconfigure in minutes, allowing the instrument to observe thousands of targets per exposure with extraordinary efficiency. The resulting maps will extend detailed three-dimensional galaxy coverage into the distance ranges where the controversial candidates reside. The Euclid Space Telescope, launched by the European Space Agency in 2023, is surveying roughly one-third of the entire sky from its orbit around the second Lagrange point. Its instruments measure both the shapes and redshifts of billions of galaxies, providing independent constraints on large-scale structure across cosmic distances that ground-based surveys struggle to reach. Euclid's wide field coverage is particularly valuable for testing the candidate structures because it will survey the relevant regions of sky with uniform sensitivity, reducing the observational selection effects that complicate ground-based analyses. The Vera Rubin Observatory in Chile, expected to begin its primary survey in the mid-2020s, will photograph the entire accessible sky every few nights for a decade, using the largest digital camera ever constructed. Its legacy survey of space and time will detect and catalogue approximately 20 billion galaxies, producing a photometric dataset of staggering size. While photometric redshifts are less precise than spectroscopic measurements, the sheer volume of data will enable large-scale structure analyses at scales and distances that spectroscopic surveys cannot efficiently reach. These surveys will test the candidate structures directly. If the Hercules-Corona Borealis Great Wall traces a genuine overdensity in the galaxy distribution, the new surveys will detect it through direct galaxy counts rather than indirect gamma-ray burst statistics. The excess should appear as a measurable increase in galaxy density at the relevant redshift in the relevant patch of sky, confirmed independently by multiple instruments using multiple methods. If the huge LQG marks a real concentration of matter, the quasars within it should be embedded in a detectable overdensity of normal galaxies at the same distance. And if the giant GRB ring outlines a shell or ring of enhanced galaxy formation, the galaxies themselves should be visible in deep imaging surveys. Conversely, if these structures are statistical illusions, the new data will dissolve them. This is one of the most reliable principles in observational science. Apparent patterns produced by small samples and incomplete data routinely vanish when sample sizes increase by orders of magnitude. The monsters that terrorized cosmology for a decade might simply evaporate under the sustained illumination of better observations, joining Lowell's Martian canals in the catalogue of patterns that the human mind constructed from insufficient evidence. Either outcome will be scientifically transformative. Confirmation of a structure spanning 10 billion light-years would trigger a fundamental rethinking of cosmological assumptions that have guided the field for nearly a century. It would demand new physics, whether in the form of modified inflationary models, revised theories of structure formation, or an entirely new framework for understanding how matter organizes itself at the largest scales. Rejection would reinforce the standard model and demonstrate that the cosmological principle holds even at the most extreme scales where it has been challenged. The verdict is not yet in. The data needed to deliver it is being collected right now, photon by photon, galaxy by galaxy, redshift by redshift, in observatories on mountaintops and in orbit above the atmosphere. Within the next decade, the ambiguity that has sustained this debate will be resolved, and the answer will determine whether the largest structures in the universe are the confirmed walls and filaments of the cosmic web, structures spanning roughly 1 billion light-years and consistent with known physics, or something far larger, far stranger, and far more challenging to explain. What those structures reveal about the origin and fate of the cosmos is where this story reaches its deepest implications. Every wall, every filament, every void in the cosmic web traces its origin to an event that lasted less than a trillionth of a trillionth of a trillionth of a second. During inflation, the universe expanded by a factor so extreme that the entire observable cosmos today grew from a region smaller than a single proton. This expansion was not gentle. It was not a slow swelling like bread rising in an oven. It was violent, exponential, almost incomprehensibly rapid. A doubling of space every fraction of a second, repeated so many times that the total expansion exceeded a factor of 10 to the 26th power, and embedded within this runaway growth were the seeds of all structure that would ever exist. Before inflation, quantum mechanics governed the distribution of energy at the smallest conceivable scales. Subatomic fluctuations, random variations in energy density dictated by Heisenberg's uncertainty principle, permeated the nascent cosmos. These were not exotic or unusual phenomena. Quantum fluctuations are a fundamental feature of reality at subatomic scales. They exist everywhere, all the time, in every cubic centimeter of space. The vacuum itself seethes with them. Under normal circumstances, these fluctuations would have remained confined to the quantum realm, invisible and irrelevant to the macroscopic universe. A fluctuation spanning 1/1000,000,000th of a meter has no consequence for structures measured in light years. The scales are too vastly different for any connection to exist. But inflation changed the rules. It took those variations on scales smaller than atoms and stretched them to scales spanning millions of light years. Fluctuations that had existed for immeasurably brief instants in a volume smaller than a nucleus were suddenly frozen into the fabric of a universe expanding faster than light. By the time inflation ended, roughly 10 to the negative 32 seconds after it began, the cosmos was imprinted with a pattern of density variations. Some regions were fractionally denser than the cosmic average, others were fractionally less dense. The differences were minuscule, approximately 1 part in 100,000. If the average density of the universe were represented by a perfectly calm lake, the fluctuations would be ripples less than a millimeter high on a body of water a kilometer deep, almost imperceptible, almost uniform, but not quite. These variations were the blueprint for everything. Every galaxy cluster that would ever form, every filament that would ever stretch between clusters, every void that would ever yawn open between filaments, was encoded in that primordial pattern of infinitesimal density differences. The blueprint was written in the language of quantum mechanics and read by gravity over the next 14 billion years. Gravity did the reading. In regions where the density was fractionally above average, gravity exerted a marginally stronger pull. Matter from surrounding areas fell inward, increasing the density further. This in turn strengthened the local gravitational field, attracting still more material from an expanding neighborhood. The process fed on itself, a positive feedback loop operating not over days or years but over hundreds of millions of years. The overdense regions grew steadily denser. The underdense regions, losing matter to their gravitationally greedy neighbors, grew steadily emptier. The faint initial pattern deepened, sharpened, gained contrast, and eventually resolved into the dramatic architecture of the cosmic web. Dark matter played the leading role in this transformation. Comprising roughly 85% of all matter in the universe, dark matter interacts only through gravity. It does not absorb, emit, or scatter light. It does not interact with normal matter through electromagnetic forces. This invisibility, which makes it so difficult to detect directly, gave it a crucial advantage in the early universe. While ordinary baryonic matter remained coupled to radiation, trapped in a hot, opaque plasma where photon pressure resisted gravitational collapse, dark matter felt no such resistance. It was immune to the radiation that held normal matter in check. It fell freely into the gravitational wells defined by the primordial density fluctuations, clumping and concentrating, while baryonic matter was still imprisoned in the plasma. Over the first few 100,000 years, dark matter built an invisible scaffolding. It collected into halos at the densest nodes of the emerging web, streamed along filaments connecting those nodes, and drained away from the regions destined to become voids. This scaffolding was complete in outline, if not in detail, long before ordinary matter could participate. The skeleton of the cosmic web was assembled in darkness, by invisible material, guided by quantum fluctuations that had been stretched to cosmic proportions by inflationary expansion. When the universe finally cooled enough for electrons and protons to combine into neutral hydrogen atoms, approximately 380,000 years after the Big Bang, normal matter was released from its electromagnetic prison. The photons that had been scattering ceaselessly off free electrons suddenly streamed away unimpeded, eventually becoming the cosmic microwave background radiation that satellites detect today. Baryonic matter, no longer supported by radiation pressure, collapsed into the dark matter structures that had been waiting for it. Gas fell into dark matter halos, collected along filaments, and accumulated at the densest intersections. Over the next several 100 million years, this gas condensed further, fragmented, and ignited into the first stars and galaxies. This sequence explains why the cosmic web exists in the form we observe. Dark matter built the framework. Normal matter decorated it. The galaxies that redshift surveys map are luminous ornaments hanging on an invisible scaffold that outweighs them by a factor of roughly 6-1. When astronomers trace the positions of galaxies to identify filaments, walls, and voids, they are mapping the visible traces of a much larger dark matter architecture that can be inferred but never directly photographed. Supercomputer simulations have become the primary tool for testing this entire picture against observation. The computational demands are extraordinary. Simulating the evolution of cosmic structure from initial conditions shortly after the Big Bang through to the present day requires tracking the gravitational interactions of billions of particles over billions of years of simulated time. Each particle represents a clump of dark matter or a parcel of gas, and each interacts gravitationally with every other particle in the simulation volume. The calculations are performed on machines occupying entire floors of research facilities, consuming enough electricity to power small towns, running continuously for months. Projects with names like the Millennium Simulation, Illustris TNG, Eagle, and the Bolshoi simulation have produced virtual universes of remarkable fidelity. Researchers set the initial conditions to match the density fluctuation pattern measured in the cosmic microwave background, specify the cosmological parameters, the amounts of dark matter, dark energy, and baryonic matter, the expansion rate, the initial power spectrum, then press start and let the laws of physics operate. Gravity pulls matter together, gas cools, condenses, and forms galaxies. Dark energy accelerates the expansion. Structure grows from the initial seeds in precisely the way the theoretical framework predicts. The results are striking in their agreement with observation. The simulated universes produce cosmic webs that are statistically indistinguishable from the real one. The same filaments appear, stretching hundreds of millions of light years between dense nodes. The same walls form, thin sheets of enhanced galaxy density separating adjacent voids. The same voids open up, vast underdense regions occupying the majority of the simulated volume. When researchers apply the same clustering statistics to simulated galaxy catalogues that observers apply to real ones, the numbers match. The two-point correlation function, the baryon acoustic oscillation scale, the void size distribution, the filament thickness profiles, all agree with observations within the measurement uncertainties. This agreement is one of the great triumphs of modern cosmology. It demonstrates that the basic physical picture, quantum fluctuations stretched by inflation, amplified by gravitational instability, shaped by the interplay of dark matter and baryonic physics, correctly describes how the largest structures in the universe formed. No exotic forces are required. No unexplained ingredients need to be added. The cosmic web emerges naturally, inevitably, from the known laws of physics operating on measured initial conditions. It is as predictable, in retrospect, as a river system carving drainage patterns into a landscape given the topography and rainfall. But the simulations also expose the boundaries of this success. They reproduce the well-established structures beautifully. Walls spanning hundreds of millions of light years, filaments connecting massive clusters, voids stretching across comparable distances, all appear at roughly the observed frequencies and sizes. When researchers search the simulated volumes for structures resembling the Sloan Great Wall or the Boss Great Wall, they find comparable features at roughly the expected rate. These structures are rare, sitting at the tail end of the probability distribution for cosmic web features, but they are not impossible. The standard model can accommodate them. The controversial candidates described earlier are a fundamentally different story. When researchers search simulations based on the lambda cold dark matter model for structures comparable to the Huge Large Quasar Group or the Hercules-Corona Borealis Great Wall, they find essentially nothing. The simulated universes, despite containing billions of particles evolving over billions of years in volumes spanning billions of light years, do not produce coherent overdensities stretching 4 to 10 billion light years. The initial density fluctuations from inflation simply do not contain enough power at those enormous scales to create such extreme concentrations. The primordial power spectrum, measured with exquisite precision from the cosmic microwave background, falls off at the largest scales in a way that suppresses structure formation above roughly 1 billion light years. Structures much larger than this are not just rare in simulations, they are absent. This absence creates a stark binary. Either the candidate structures are not real, and the simulations correctly predict the maximum scale of cosmic architecture, or the candidate structures are real, and something fundamental is missing from the standard model. There is no comfortable middle ground. Several theoretical proposals have been advanced to fill the gap if the structures prove genuine. One class of proposals targets inflation itself. The simplest inflationary models assume a single quantum field, the inflaton, rolling smoothly down a potential energy surface. This smooth rolling produces a nearly scale-invariant power spectrum, meaning density fluctuations of roughly equal amplitude at all scales. But more complex inflationary models allow the inflaton to experience bumps, steps, or phase transitions during its descent. These features would imprint additional power at specific scales, boosting density fluctuations at those scales while leaving the rest of the power spectrum unchanged. If a feature in the inflationary potential happened to enhance fluctuations at scales of several billion light years, it could make structures like the huge LQG or the Hercules-Corona Borealis Great Wall statistically possible without affecting the well-tested predictions at smaller scales. Detecting such features requires measuring the power spectrum of density fluctuations at the largest accessible scales with extraordinary precision. The cosmic microwave background provides the cleanest measurement, but its angular resolution at the largest scales is limited by the finite size of the observable universe. There are only so many independent patches of sky at the largest angular separations, which means the statistical uncertainties are inherently large. Galaxy surveys provide complementary information, but they too face statistical limitations at the largest scales. The signal being sought, a subtle enhancement of power at multi-billion light-year scales, may be too faint to detect with current or near-future instruments. Another class of proposals involves modifications to gravity. General relativity has been tested with remarkable precision in strong gravitational fields, near neutron stars and black holes, and at solar system scales, where satellite missions have confirmed its predictions to parts per billion. But its behavior at cosmological scales, across distances of billions of light years, is constrained less directly. Observations of cosmic expansion and structure growth are consistent with general relativity, but they do not test it with the same precision achieved at smaller scales. Some alternative gravitational theories predict deviations from general relativity that become significant only at the largest distances. If gravity is slightly stronger than Einstein predicted at scales of billions of light years, the enhancement would amplify structure formation, potentially producing larger and denser concentrations of matter than the standard model allows while leaving predictions at smaller scales untouched. Dark energy introduces yet another variable. In the standard model, dark energy takes the form of a cosmological constant, a fixed energy density woven into the fabric of space itself, identical everywhere and unchanging over time. But the cosmological constant is only the simplest possibility. Observational constraints allow dark energy to vary, both in time and potentially in space. If dark energy is slightly weaker in some regions and slightly stronger in others, it would create an uneven playing field for structure formation. Regions with below-average dark energy would experience less resistance to gravitational collapse, allowing matter to concentrate more efficiently and potentially forming structures larger than the cosmic average. Detecting spatial variations in dark energy requires precisely the kind of wide-field, deep galaxy surveys that the next generation of instruments will deliver. Whatever the theoretical explanation, the stakes extend far beyond resolving a debate about specific candidate structures. The largest patterns in the matter distribution are direct fossils of conditions that existed during and immediately after inflation. They are imprints of physics that operated during the universe's first fraction of a second, preserved in the positions of billions of galaxies observed 14 billion years later. Measuring these patterns constrains what happened during cosmic genesis with a directness that few other observations can match. Every filament, every void, every wall encodes information about the quantum field that drove inflation, the initial spectrum of density fluctuations, and the subsequent interplay of gravity, dark matter, and dark energy across cosmic time. The cosmic web is a message written at the beginning of time, and we are only now developing the instruments to read it completely. The future of this architecture is governed by the same dark energy whose properties remain so uncertain. Under the current standard model, where dark energy is a cosmological constant, the cosmic web faces a long, slow dissolution. The expansion of space is accelerating. Every region of the cosmos that is not gravitationally bound, meaning every structure larger than the most massive galaxy clusters, is being carried apart at speeds that increase over time. The filaments connecting clusters are being stretched, the walls separating voids are being thinned, the voids themselves are expanding, swallowing surrounding structure as their boundaries push outward. This process is already underway. The cosmic web we observe today is slightly more diffuse than it was a billion years ago, and it will be slightly more diffuse a billion years from now. The changes are imperceptible on human timescales, but projected forward over trillions of years, they are catastrophic for cosmic architecture. Filaments will thin until they contain too few galaxies to be detected by any survey. Walls will disperse into uniform backgrounds, indistinguishable from the voids they once separated. Galaxy clusters, the densest nodes of the web, will persist as gravitationally bound islands, but the bridges between them will vanish. Each cluster will sit alone in an expanding ocean of emptiness, separated from its nearest neighbor by distances that grow without limit. Simulations of this far future paint a stark picture. Approximately 100 billion years from now, the observable universe from any given galaxy cluster will have shrunk to contain only that cluster's own bound members. Every other structure, every other cluster, every distant galaxy will have been carried beyond the cosmological horizon by accelerating expansion. Light from those objects will be redshifted to wavelengths longer than the observable universe itself, rendering them permanently invisible. The cosmic web will not merely be difficult to detect, it will have ceased to exist as a physical structure. This erasure carries a deeply unsettling implication for any observers who might arise in that distant era. A civilization born trillions of years from now, in a galaxy orbiting within an isolated cluster, would find itself surrounded by emptiness in every direction. No filaments, no walls, no neighboring clusters visible at any wavelength. The cosmic microwave background, already faint today at a temperature of approximately 2.7 Kelvin, will have cooled to temperatures so far below detection thresholds that no conceivable instrument could register it. The baryon acoustic oscillation imprint, that subtle statistical excess at 490 million light-years, will have been stretched beyond recognition as the galaxies that once traced it scatter into invisibility. Such a civilization would possess no observational evidence that the cosmic web ever existed. It could not discover the large-scale structure of the universe because that structure would be gone. It could not infer the Big Bang from the cosmic microwave background because that radiation would be undetectable. It could not measure the expansion of the universe because no distant galaxies would remain visible to serve as recession velocity markers. The fundamental discoveries of 20th and 21st century cosmology, the expanding universe, the cosmic microwave background, the cosmic web, dark energy, would be permanently inaccessible to any observer relying on electromagnetic radiation. We live in a cosmologically privileged epoch. The cosmic web is visible now because the universe occupies a narrow window in its history. It is old enough for gravity to have sculpted the primordial density fluctuations into the intricate architecture of filaments, walls, and voids. But it is young enough that dark energy has not yet torn that architecture apart. This window opened roughly 1 billion years after the Big Bang, when the first large-scale structures became detectable, and it will close gradually over the coming tens of billions of years as accelerating expansion disperses them. The window spans perhaps 50 billion years in total, a generous interval by human standards but a slender fraction of the universe's infinite future. We happen to exist within it. This temporal coincidence is not anthropically selected in any obvious way. The existence of observers does not require the cosmic web to be visible. Stars can burn, planets can form, and life can evolve within an isolated galaxy cluster, just as readily as within a connected cosmic web. Future civilizations will lack cosmological context, but they will not lack physics or chemistry or biology. They will simply be cosmologically blind, living in a universe whose grandest structures have been erased by the same expansion that once helped create them. And this brings us to what may be the most remarkable dimension of the entire story. The largest structures ever observed or proposed in the universe, patterns spanning billions of light-years and containing the organized positions of millions of galaxies, were discovered by a species that has existed for roughly 300,000 years on a single rocky planet, orbiting an unremarkable main sequence star in an outer arm of an ordinary barred spiral galaxy. Modern astronomy, the discipline that made these discoveries possible, has existed for approximately 4 centuries. Digital sky surveys, the technology that revealed the cosmic web in its full extent, have existed for roughly 3 decades. The entire edifice of large-scale structure research, from the first CFA redshift measurements to the latest data releases from the Dark Energy Spectroscopic Instrument, fits within a single human lifetime. In that infinitesimal sliver of cosmic time, using instruments assembled from silicon, aluminum, and glass, materials forged in the interiors of stars that died before our solar system formed. Humans mapped the cosmic web. We identified statistical patterns in the three-dimensional distribution of galaxies that span distances so vast that light itself requires billions of years to traverse them. We developed mathematical tools rigorous enough to distinguish genuine structures from the phantom patterns our evolved brains reflexively impose on noisy data. We built computer simulations containing billions of particles that recreate the growth of the cosmic web from quantum fluctuations to galaxy clusters, confirming that our understanding of gravity, dark matter, and the initial conditions of the universe is fundamentally correct. We even found candidate structures so enormous that, if real, they would overturn assumptions that have guided cosmology for a century. The Hercules-Corona Borealis Great Wall, spanning an estimated 10 billion light-years, remains unconfirmed. It may prove to be a statistical artifact that dissolves under the scrutiny of deeper surveys, or it may prove to be real, demanding new physics and forcing a radical revision of the cosmological principle. The huge large quasar group and the giant gamma-ray burst ring occupy the same uncertain territory, too significant to ignore and too ambiguous to accept. The confirmed record holders are impressive enough. The Sloan Great Wall, at 1.37 billion light-years, stands as the largest well-established structure identified through direct galaxy mapping. The Boss Great Wall, at approximately 1 billion light-years, reinforces the picture of a cosmos organized on scales that push against, but do not unambiguously break the homogeneity threshold. These are not speculative candidates inferred from sparse samples of exotic objects. They are measured concentrations of hundreds of thousands of galaxies, mapped in 3 dimensions with spectroscopic precision, confirmed by independent surveys and consistent with the predictions of supercomputer simulations. They are real, and they are enormous. The final answers about the controversial candidates will come from data that is being gathered at this moment. Photons that left distant galaxies billions of years ago are arriving tonight at focal planes in New Mexico, in Chile, and in orbit around the second Lagrange point. Each photon carries information about where its source galaxy sits in the cosmic web. Each measured redshift adds one more point to the three-dimensional map. As the maps grow denser and deeper, the ambiguities that have sustained the debate over the Hercules-Corona Borealis Great Wall and its fellow candidates will narrow. Within the coming decade, the evidence will either confirm these structures or dissolve them. The outcome will reshape our understanding of cosmic architecture either way. But regardless of where that verdict falls, the search itself has revealed something profound. The universe is not a formless void sprinkled randomly with luminous points. It is organized. It possesses architecture on scales so vast that human language strains to describe them. Filaments stretching hundreds of millions of light-years connect nodes containing thousands of galaxies. Walls thinner than their own length by factors of 10 separate voids that occupy the overwhelming majority of cosmic volume. And threading through this architecture, invisible but dominant, dark matter scaffolding outweighs the luminous galaxies it supports by nearly 6 to 1. The cosmic web does not care about human significance. It is a pattern in matter, governed by gravity, shaped by initial conditions that were set during the first trillionth of a trillionth of a trillionth of a second of cosmic existence. It preceded Earth by roughly 9 billion years. It will outlast the Sun by tens of billions more, though in progressively faded form. It was not built for us. It was not built for anything. It emerged from quantum randomness amplified by the patient, implacable work of gravity across cosmic time. And yet, a species on one world, in one galaxy, in one filament, within one supercluster, looked outward. It counted galaxies. It measured their distances. It plotted their positions and recognized the pattern. It built machines that reproduced the pattern from first principles, confirming that the laws of physics, discovered in laboratories on that same small world, govern the formation of structures spanning a significant fraction of the observable universe. In a cosmos where approximately 90% of the volume is void, where the overwhelming majority of space contains almost nothing, the fact that matter organized itself into galaxies is remarkable. The fact that galaxies organize themselves into a web is more remarkable still. And the fact that one species, confined to one planet for the entirety of its existence, figured out the architecture of that web using nothing but ingenuity and the light that happened to reach its telescopes, may be the most improbable structure of all. The largest structure in the universe might be a confirmed wall of galaxies stretching 1.37 billion light-years, or it might be a contested colossus spanning 10 billion, awaiting the verdict of instruments now scanning the sky. Either way, we found it. From inside the web, blinded by dust, limited by the speed of light, confined to a single vantage point in a cosmos containing 2 trillion galaxies, we found it. That is not nothing. That is the universe becoming aware of its own architecture. And for this brief window in cosmic history, before dark energy stretches the evidence into oblivion, that awareness exists. It is here, now, reading these words, contemplating structures so vast they dwarf everything that has ever been built, imagined, or dreamed by every civilization that has ever existed or ever will. The cosmic web was not built for us, but we are the ones who found it, and in finding it, we discovered that the universe is stranger, grander, and more intricately organized than any previous generation of humans could have imagined. The search continues. The data keeps arriving, and the architecture of everything keeps revealing itself, one galaxy at a time, one redshift at a time, one discovery at a time, to a species still learning to read the blueprint of creation.